Thank you guys, and welcome to my talk today. And my name is Jia, and today I'm going to talk about how we can bring geospatial support to Apache Iceberg. First of all, you guys can all hear me from the back, right? Awesome. All right, so if you guys have been following the Iceberg mailing list, so there is a email thread has been talking about the geospatial support in Iceberg, and also we have a Google Doc already created, and we also have a GitHub issue created and describe what we want to do in this particular proposal, right? So today I'm going to talk about those details and give you an overall idea about what we're going to propose in this proposal. So, and I'm from Variables, and just a little bit about me. So Variables is a cloud data warehouse for spatial intelligence, spatial analytics, and AI. And I'm a co-founder of Variables, and I'm the PMC chair of Apache Sedona, which is a very popular open source distributed compute engine for geospatial data. And I was a professor of database at Washington State University at Pullman. All right. So first of all, let's talk about geospatial data. So first of all, what is geospatial data? So in fact, geospatial data is everywhere. So, and as you can see from here, you can see geospatial data on a daily basis. So the telemetry data collected by our GPS devices, by our mobile phone, right? And also the satellite imagery data captured by our satellites, which are monitoring our planet 24/7. And also, you know, the modeling service data and the residential maps, as well as traffic data, as well as LiDAR data, all those kind of things, as long as they have spatial coordinates, longitude and latitude, so they can be considered as geospatial data. And geospatial data could be really, really big. So for example, so those kind of mobile devices, they generate millions and billions of GPS sensors, GPS signals every day. So right now, as you know, so we have over 5 billion mobile devices all over the world. And also there are many open source and public road network data. For example, OpenStreetMap data. So they publish new data. They have over 1 terabyte road network data, which is public available. And they got updated on a daily basis. And also, NASA has released over 22 petabyte satellite imagery data, and which is also open to the public, and you can download that and analyze that, right? So geospatial, in short, geospatial data is everywhere, and they are very big. Now, so let's talk about, so what are the geospatial data model or geospatial data type? So in general, there are 3 types of geospatial data. So first, we call it vector data, and the second one is called imagery data or raster data. The third one is called multidimensional array data. So the vector data is probably the most common one you have seen so far. So that is, longitude, latitude, point, polygon, line string, trips, trajectories. So those are the vector data. So basically, they describe the shape of the geometry objects. And the imagery data, raster data, so they are just image captured by satellites or drones, right? So they usually come with a small picture together with the georeference information, including the bounding box of this image, which indicates which region this image is describing. And the multi-dimension array data, so it usually has a multiple dimension. For example, it can have a third dimension called timestamp, and you can have multiple observation stacked on top of each other. So that is the multi-dimensional array data. So in our bring geo to Iceberg proposal, we in particular want to focus on the vector data part. So we want to do things step by step. Otherwise, things get very complicated and it will never pass through. So we actually, at Variables, so we actually already did a spatial extension on top of Apache Iceberg in our own Iceberg fork. And in our Iceberg fork, we did 2 things. We extend Apache Iceberg to support vector data, so those geometry type data. And on the other hand, we also extend Iceberg to support raster data, the raster images. So we have been working on it for a while. And so now the product has kind of become mature, and we decided to donate that to the Iceberg community. And we are working with a few Iceberg PMC and try to formalize this extension we made and make it to the Iceberg. So just a quick overview about what we did in terms of data model in our Iceberg fork called Havasu. So first, we store the geometry data as a geometry type column, and you could store point, polygon, line string, this kind of object in the same column, and there is a type called geometry. And there's another one called raster. This is called raster type. So in this raster type, so we actually do not store the raster images themselves. We actually store the reference to the, store the URL to those raster image, because those raster image usually are very big and you don't want to create another copy of those raster images in your Iceberg table. So with all this in place, so we also extend the expression partition transform in Iceberg. So basically, you will be able, with Havasu, you will be able to perform together with our Sedona and Spark engine, you'll be able to perform these two operations, for example. So you can directly insert geometry data into Iceberg table, for example, like this one. So you insert a geometry column, geometry value, you get it from stgeom from text. And after the data insertion is done, you can perform queries as well. You can directly perform query like join queries on this kind of geometry column, like this, right? You can, so we have two geometry column here, and we have st intersect predicate to trigger a spatial join on the geometry type column. So basically, this is the final outcome we want to achieve, which already achieved in our Iceberg fork, but we want to also achieve that in the official Iceberg repo. Okay, now let's talk about the details of the proposal itself. So first of all, we are working with a few Iceberg PMCs, in particular Sihong, Anton, and Russell. And so there is a GitHub issue already there. And so in this proposal in particular, we want to focus on vector data, or in other words, geometry or geography data type. And so inspired by this, so there is another PR created on the Parquet community, on the Parquet format repo. So it's also trying to add geometry type to Parquet. So if you guys are interested, you can also find it on the Parquet format GitHub repo. And so we also, in this proposal, so we also borrowed lots of ideas from the GeoParquet project. So the GeoParquet project is a kind of community project. So what it does is, since Parquet does not have a native geometry type, so there is a community that's trying to add a geometry type to Parquet. And so they formed this community called GeoParquet, and the variables is a part of that community. And now, since the Parquet community wants to add native geometry type, so we are also helping Parquet community to add this geometry type into Parquet. So basically, there are kind of two things going on at the same time. And hopefully, if the geometry type in Parquet PR get accepted, so we're gonna, like, our Geo in Iceberg proposal can also improve, become easier a little bit. So in this proposal, we decided to do this in two phases. So phase 1 and phase 2. So in phase 1, we want to focus on really basic things to make sure to find the common ground everybody can agree upon, right? So we do the following things. So physical type, so which describes the encoding of the geometry data. We also do the logical type and of course the table properties for the geometry type, and also expression as well as partition transform. So this is for phase 1. And for phase 2, so we want to do two other things, but it also depends on whether the geometry in Parquet PR can get accepted or not, right? So if that get accepted, so we can change it, like we can use this strategy here, but if it gets rejected, so probably we have to add more complicated encoding kind of stuff. But today I'm going to mostly focus on the phase one stuff. Okay, the basic physical type, logical type, expression, and partition transform. All right. So first, physical type encoding. So as you already seen before, so if you want to describe the geometry vector data, right? So these are point, polygon, length string, and they are actually multi-polygon, multi-length string. There are about like 7 different geometry subtype under the geometry type. So we want to describe that in this Iceberg geometry type. So for the physical type of the geometry data, so we store it in binary type. So we use a binary encoding called WKB. So it represents well-known binary. So it is a very classic and popular binary representation of the geometry vector data in the geospatial community, right? So there are tons of different reader and writer of WKB, right? So what it does is very simple. So it describes, so how would you store point, the longitude, latitude in the binary. And if you have a polygon, so how would you store this polygon in this binary? And so actually things can get actually very tricky because in some cases, a polygon can have internal hole, So it also describes when this happens, so how would you store this kind of nested geometries inside a binary representation? But in short, so WKB is a very popular binary representation. So we decided to use that in the for the physical type of the geometry. And it is very obvious that so use the binary type, there is some downside, right? So the downside is so Parquet won't be able to collect statistics automatically, right? So we have to do something else to make either Iceberg or Parquet to be aware of those geometry representation. So we're going to talk about that later, and that also relies on the Parquet geometry PR we mentioned before, right? So if in that PR, people actually try to allow Parquet to collect native statistic for the geometry data. Cool. Logical type. So we're going to add one type logical type. We're going to add one logical type geometry type to Iceberg, and that is corresponding to the physical binary type we use. And in this particular logical type, we also want to add a bunch of properties. So initially in our proposal, so we were trying to add, there are a couple properties we want to add, right? But we received lots of feedback from the community, and we eventually decide only add 2 minimum properties in this geometry logical type. So 2 things. One is called CRS, coordinate reference system, and the second thing is the edges. So basically, these 2 properties defines two things. The CRS describe what is the coordinate reference system of all your coordinates. So for people who are not familiar with geospatial data, right? So the longitude, latitude, you have been dealing with on a daily basis. So they are in a CRS called WGS84 or CRS84, right? So it is, so for longitude, it is like, for both of this value, they are ranged from -180 to +180 and -90 to +90, right? So they're within a specific range. However, so in the geospatial industry, there are hundreds of different coordinate reference systems. People invent those coordinate reference systems is to better describe the coordinates that are localized to their region, right? So WGS84 is a great coordinate reference system, but it will show some inaccurate result when you perform some localized operations for some specific spatial region. So that's why people invent all those kind of different CRS, but it is super hard to support all different CRS in this geometry type initially in phase 1. So people have lots of different concerns. So we decided, okay, so in phase 1, for the CRS property, we only allow the CRS84 coordinate reference system, right? And the second thing, edges. So edges indicates whether the coordinates and the corresponding operations, spatial operations you're operating on is in a planar space or it is in a spherical space. And the reason is that, so imagine, so for the geometry object that are located on the planet, right? So our Earth is not a planar space, right? So it has a spherical space, and if you want to have very accurate spatial operations and like distance calculation, spatial relationship calculation, you better have spherical some spherical operations, right? So this edge property is used to describe whether the data and operations for this property should follow the planar space operation or the spherical space operation, right? So again, it is super hard to perform spherical operations on all type of geometries, and it is hard. And so we decided to make things easier. So in the phase 1, we just support planar space calculation. So assume everything is in a planar space and you just perform regular computational geometry operations on the geometry object, right? So that's why we have these two properties. And in phase 1, although we have these two properties, so we decided to make this immutable. So people don't have to change it. Otherwise, like if someone change it to different values later on, if we want to support different CRS or different edges, it's going to be a problem, right? So in phase 1, we just add them and don't allow people to modify that. And we assume those are default values for the geometry type. All right, so, okay. So there are some technical reasons, right? So why we don't support that, but I'm gonna skip that so if you guys have questions, I can talk about that later. Okay, another thing is the expressions, right? So once you have the geometry type, then you can, your engine can perform operations, expressions on the Iceberg tables on the geometry type column. So in this proposal, we also want to, in particular, add 3 different expressions: ST intersects, ST covers, and ST covered by. So among the 3, ST intersect is absolutely necessary, and the other ST covers and ST covered by, they are optional. So the idea of ST intersect is that, so ST intersect is a very, very popular spatial expression. So what it describes is that, so it takes 2 operands, so A and B, right? It tells you that if A intersects B, and it returns true or false. That's it. So that's the definition of ST intersect. So of course, the object A and B could be very complicated, could be very 2 big polygons, and you're going to have to decide whether they actually intersect or not, right? But basically, we introduced the 3 operations, 3 expressions here, and once Iceberg detects there is a ST intersects, right? It's going to decide to go through partition transform, and it will filter out the data, and it will only retrieve the data that is really needed for this ST intersect operations, basically for filter pushdown. Cool. Final thing, partition transform. So as you already know, so partition transform is a very cool feature of Apache Iceberg, and it basically describes a one-to-one relationship between a row and a partition, right? So that way, if you have a expression of query, you can directly jump to the partition that possibly contains the data, right? And you fetch the data, and then you can do some sort of like a refinement and get the exact data you want. So we also want to do that for the geometry type data. So remember that, so this partition transform requires that there is a one-to-one relationship between a row and a partition, right? So right now, there are many techniques can generate this kind of partition ID or ID for geospatial data as well. So there are many of them, like GeoHash, Google S2, Uber H3. So basically, for example, you take a 2-dimensional point, right? It generates a one-dimensional ID for you, and so those one-dimensional ID, it sort of preserves the spatial proximity of the 2-dimensional point. So that's the idea of this kind of existing technology that can generate ID for geometry data. However, things get much trickier when it comes to the non-point data. When you have polygons, when you have trips, trajectories, right? It is really hard for this kind of technique always generate a single ID for this kind of non-point data, right? So like what usually end up happening is that, so give a polygon, it generates a bunch of ID. The cell indicated by those IDs actually covers that geometry, that polygon, or that line string, right? So it is so hard. So right now, these technologies cannot be used to solve the partition transform for geometry data. So there is another technique called XZ2, extended z-order curve for 2 dimension. So this is a very old technique, I would say. So it was invented about 2 decades ago to solve this exact same problem. So basically, it can always guarantee that it always generates a single ID for any geometry object, including polygons. Okay, so currently that is the only solution we have that can solve this problem. And unfortunately, so this XZ2 curve only works for planar space. And there is another proposal. So once so we have this bring Geo to Iceberg proposal, there is another follow-up proposal from Google that actually try to improve their S2 encoding to help to basically have the same property of XZ2. So we are still reviewing that proposal, and that could be introduced in phase 2, right? And if you guys are interested, you can also review that proposal. It requires a little bit of math to make sure it always yield a single ID for any non-point geometry. All right, so any questions so far? I know there are lots of meat here.
A couple questions from this slide.
Mm-hmm.
There's something about properties, right?
Yep.
Yeah, you said those properties are, you can't change them, right? Like it's immutable. Are those table properties?
Yes, those are table properties.
Okay, and the immutable is enforced for, like, how are you enforcing the immutable table properties?
Yeah,
I think that's like a new concept in my opinion, right? Like, because most table properties you're gonna like change, switch out.
Yeah, that's a good point. So right now we only specify that in the spec. So like you should not change it. You should not change it. Like.
So it's like a spec. Like if you're working with this, don't change these.
Yeah. And we also like it is kind of like we also like still we haven't decided this yet. We also want to make it kind of like optional. So which means if your logical type does not have these 2 properties, it defaults to, it means that it is in CRS 84. It is in, its edge is in planar space.
So how can one represent an iceberg table working with you? Like how do I, if there's a table, there's an iceberg table with like geometric types, right? I'm guessing whoever's reading an engine or something, how does it know that it's like it's our...
Yeah, that's a really good question. So as you know, so Iceberg table, like it is not standalone, right? You need to use it with the engine. So the engine has to support the geometry type. If the engine does not understand it, then that's a problem, right? Yeah. Like, so in this proposal, so actually, so everything I talked about so far, it is actually the kind of the first part, of course, the most important part of the proposal. But in the second half of the proposal, we actually also proposed that how could we introduce integration with Iceberg and Spark together with Apache Sedona, right? Because Spark does not have a geometry type, Sedona adds the geometry type to Spark. So how could we add also an integration to this proposal. So like when people have it, when this proposal gets merged, so people can use it immediately with Spark as a like first implementation. Yeah, go ahead.
You are extending that expression delivered from Iceberg.
Yes.
Are there any other like major areas you guys are building on top of? Like just other areas within like a project they're building on for this use case, or?
Like you mean the engine side? Oh.
Just on the Apache side, like just on table format, right?
Right now, so we actually also did a couple improvement to the Iceberg table. So, but they don't change the table format per se. So we allow people to use this statement called create spatial index. So it basically allow users to order the spatial data using Hilbert curve or the other curve. So that way the data is, it is clustered, and when you do filter push down, so the data will be more organized, and you can fetch less data. Yep.
What's another example of it? Trying to understand.
You mean covers and covered by?
No, just like what is an iceberg expression?
So I'm
like what you're adding these three expressions, right?
uh-huh.
To iceberg.
Uh-huh.
So what is an iceberg expression?
Oh, that's a good question. I'm not really familiar with the details here. Yeah. Yeah. So basically, what we like what we're trying to do is that, so once we have this expression, we want to actually convert it to a result to use the partition transform. To use a part. Like yeah, it is kind of like UDF. Yep. Cool. So that's a good point. So that's also another reason why we want to make it immutable, at least in phase one. Like at least we recommend people don't change the value of the properties. So the reason is that, so right now, we don't want to allow geometry data that has in the same column or same table has different table properties. Say some of them have planar space operations, some of them have spherical operations, some of them have WGS84 CRS, some of them have different CRS. So this will lead to wrong curve result because of partition transform. And in the future, if you have min-max statistics, those will also lead to wrong result. So those information are immutable.
But all of those things are like at a field level generally, right? Like even if you say, hey, stats, you have like separate stats for like field. So do these properties make sense to have them at the field level, still immutable, but like have them at the field level, not at the table level?
Yes, that's a good question as well. So when we initially start this, right? So we actually don't want to put this in the tape as a table properties. We want to put as field level, or we want to even put in the parquet level as the parquet metadata, right? So we talked to Anton and Ruan for that, and they kind of want to have this as a table properties. The reason is simple, because first of all, so these are the properties applied to the entire table, right? You don't want to allow different values for the same table.
That might be like a short-term thing, like where you want to like keep it simple and then you want to like not allow it. But like if you put it in the table level, like you are just cornering yourself. Like when we want to like expand this support to say, hey, in the same table I can have like two geometrical fields each of these things might have like a different different property. So if you say, hey, I want to keep it simple, I don't want to allow this in the same table, we can put some restrictions on like, okay, with the table creation time, you can say, hey, I'm going to put this restriction of like 2 fields. If they are in the same table, they have to have the same properties, just like how we said, like, okay, we're going to make it immutable. Like that way it gives us like opportunity to add that in the future. But like versus if you add at the table level, then it becomes like a breaking spec change.
Yeah, yeah, yeah. That's a really good point, right? So yeah, so I think we can go back and think about that, right? And also like folks, if you have comments, please feel free to like follow up in the proposal and also on the Iceberg mailing list, right? So we have been waiting for feedback for quite some time, and I know there are lots of proposals out there, and the people just are really busy, right? But we really want to have feedback from the community, right? So we can then modify the proposal and improve it, right? All right, so let's move on.
So just to complete that thought, where you guys are coming from is that geospatial data qualifies to be its own table, and that's why you have a logical type table properties for that logical type, and one geospatial data to be present in one table, right? Like that's how you're thinking about it.
Yeah.
It's a special kind of a table where geospatial data is stored and it is partitioned for the type that is given, and that's how you're also enabling your expressions and all of that for helping with partitioning, navigating through the partitions.
Yeah, yeah.
That's the complete stereotype of a table.
That's true. That's true, right? So, but like if you have, I wouldn't say this table is really special. You can still you can still perform non-spatial operation on this table. It just have a geospatial column, geometry column there.
So I don't think he's saying that, right? Like it's saying like, okay, a table can have a geospatial fields, and you can use that field for partitioning that particular table also. Like
Exactly.
That's what we are saying.
Yeah, you can do something else as well. You can partition with other field.
If that's not the right partitioning scheme for that particular data, I would use some other field for partitioning. It's not a special table only for like this geospatial.
Yeah, exactly. Yeah.
Then I think what we said makes sense, where each column has its own.
Yeah, I think that's really good suggestion, I think. Yeah. Although that is not that common, but I think there will be cases that, okay, so you're gonna have multiple column there. Yeah, that's a really good point. All right, let me speed up. So in phase 2, so couple things we want to consider is the B-box statistics for the geometry type column. So, but it also depends on if the Parquet geometry type going to be accepted or not, right? Because in that Parquet PR, it wants to add this statistic called bounding box, right? So it has the mean and max for X and mean and max for Y, so on and so forth.
Will there be any like properties or settings for like the in which needs to go in the Parquet itself? Like,
so so actually in that PR, so in that PR, it actually tries to add several more properties, like the CRS, the one that I mentioned, and the edges, and there is also Apple, and there is another one. There are about like 4 or 5 properties they want to add in that PR. So then if that get accepted, then that's going to become in the Parquet metadata level, right? So we can actually use those information directly. Yeah. But I mean, that PR could take a really long time to get in. Yeah. All right. Yeah, so in phase 2, another thing we want to consider is the spherical data support, right? So we allow edges to be spherical. All right. Any other final questions? Yeah.
What are your thoughts on vectorized query execution on the spatial types?
Yeah, so this is really good idea, right? So so the binary encoding here, we use WKB, right? So that is not good for vectorized execution for sure, right? So in our proposal, so there is another appendix that accurately describe other possible encoding for the geometry for the geometry data, physical encoding, right? So that could actually facilitate the vectorized query execution. However, there are lots of different opinions on that. So if we see lots of different opinions. So eventually we decide we put it aside. So if we want to choose one encoding there, it will take forever to get this pair to make this pair pass through.
Because I'm thinking of like, reading the data into arrow buffers, right, and then processing it that way.
Yeah. So there is a couple different way to describe this geometries, right? But things get really complicated, like I mentioned. Things get really complicated when you have polygons, and when you have because there could be multi-polygons, and these two polygons belong to the same object, and you could also have one polygon inside another polygon. How could you describe all that in a data structure that honors vectorized execution, but also some sort of like benefits the compression, right? So we have three different encoding techniques mentioned in our proposal, and the Variables also conducted a very comprehensive performance benchmark on that, like whether the vectorized encoding will improve the scan performance, and also how would those different encoding affect the compression rate of the Parquet data file, right? So yeah, that's about that.
Is WKB like self-describing? Does it say whether or not it's planar or spherical?
No. So I mean, it does not say whether it is planar or spherical. It is self-describing in the sense that it tells you if this is a point, if this is a polygon, if this is a multi-point. So it contains this kind of information. But it does not tell you if this is planar space or spherical space. And it also does not tell you that which CRS it is in. Yep.
Can you also talk about from your point of view, how you are going to use it, and what are the use cases which you are solving by doing this?
Yeah. Also great point. So I was not I didn't expect a lot of people are interested in what are the applications and use cases for that, right? So this is actually the main business of our company. So we use Iceberg tables as a underlying storage, like open data format. And so we have lots of customers have interesting use cases. So they have their data stored in, say, in Databricks, say in Athena, in Snowflake, right? So, but they want to perform spatial operations, for example. So they have billions of GPS trips, right? They want to find out, so what are the GPS trips inside each of the city boundary or city blocks, right? They want to count the hotness of each city blocks, right? This is a very simple example. They want to build some sort of heat map for that.
So it's mostly visualization purposes, analytical visualization purposes. Is that where you see a lot of value, at least what you are handling right now?
Yeah. So in our use case, at least in our in the business our company, so we mainly focus on analytics use case, right? But there are, of course, lots of real-time analytics use case, like transactional use cases, right? So the data you collect from the GPS trips, right? So those are actually real-time information, streaming data, and you want to store it somewhere. You can use Flink actually, and Sedona also has a support on Flink.
The expressions which I see right now, are they mostly solving the analytical needs of it?
Yes.
Or are they going to solve operational needs too?
Right now, we mostly focus on analytics, and in this proposal, we mostly focus on solving analytics use cases, right? So, but you have data and you want to run analytics, every few hours or every day or every week.
Just one high level question, but before your company, how are customers getting past this problem? Are there already any kind of database vendors or solutions out there? Because I don't really know that much in the lake space. I'm just curious in maybe the older warehouse space, if any systems had like, you know, support for like geospatial type?
Yeah, that's a really good question. What this gentleman is asking is that, so before Iceberg exists, before this proposal, what are people doing, right? Geospatial data has been there for decades. So this, like, how to store geospatial data efficiently and also in a clean format, and also share that with other people. It is a pain in the ass for decades. Yeah, so like that's why people invent WKB. So people they want to store WKB, like store geometry data in WKB format, in a binary format, share with others. But there are, I think, over 50 different formats out there that describe how you should store geospatial data. And so there is a very popular project in the geospatial industry called GDAO. So this project has hundreds of thousands of GitHub stars and like tens of thousands of people use it. The only purpose of this project is to help you read geospatial data. Read and write geospatial data. Yeah, it is so hard. That's why we come in and there is a community, right? So we really want to stop this, right? So we want to enable that. So like we use a unified format that we don't have to keep copying data, make different copies and import data from really different formats. Yeah.
Is there any AI engines work on this kind of maths?
You mean other kind of engine?
Yeah, I mean PyTorch, Ray, or something. Work on that.
You mean like machine
Learning? Yes.
Right now, I don't think so. I don't think so. So, what I have seen so far is that there are lots of cloud vendors, cloud data warehouse. They have this kind of geospatial support, but for machine learning use cases, that's sadly not people are aware of that. But in our company, we are building machine learning on top of this geometry type. So we allow users to directly run segmentation, classification to extract the road segments, objects, buildings, weather events from the satellite images from the geometry and raster data type, and you can join that with other vector data. All right, I think time's up. We have another speaker there. So just one last thing. So our company is hiring, and yeah, sorry about that. So our company is hiring, and we hire like from senior to principal level database engineer, backend, cloud, DevOps engineers, and we just closed our Series A. We have tens of millions dollars in bank. So we are aggressively hiring. We have offices in San Francisco and Seattle. Thank you, guys. Good.